Juggle so many different tools just
I
to get
cannot hear
work
you.
done. A simple task turns into a time-consuming mess because work sprawl has scattered the tools and context we rely on. And the trend towards bundling software isn't
Can you
addressing
please
the
give
root of
me
the problem. The system's broken, and it's wasting our time.
indication that you
8
can
years
hear me?
ago, we started ClickUp with a mission to save people time from switching between a bunch of different applications. But we knew the
Okay,
answer wasn't just
so,
bundling a bunch of tools together. We needed to
I see a
rethink how
picture.
software was built entirely.
I
To solve the
will
root of the problem, we built a single, flexible platform with powerful primitives that can be shared to build multiple first-class products inside of one app.
Well,
We
first
call
of all,
this convergence.
thank you
It's
very
allowed
much
us to
for the
deliver products
invitation
at an
to
extremely
contribute
high
to
velocity.
this,
And now
conference.
we're
I'm
tying
very
it all
honored,
together
to
in a
join
new way.
your conference
Everything we've
and
built
show,
has led to this.
what we are
Introducing
doing, what we have
ClickUp
already
4.0.
done,
The
especially
first
also to
converged
very
AI
much
workspace
for
in the
the
world.
nice
It's the
introduction
future
my
of software. It's not just another bundle of
So,
apps. It's a fundamentally converged
as you
platform
told,
where everything works together
I'm an old guy
seamlessly.
who is very
From communication.
networks. What is the motivation to deal with power quality? And I will also tell you something about power quality monitoring. Why is this so important? Because we have seen that incidents or issues with the power quality, bad power quality, or disturbances can lead to dramatic outage costs and also damage costs. I have here added 2 pictures from our work, which we have done with industrial clients. You see in the top of the on the top of the picture a damage generator, of course with significant damage costs. Nevertheless, those the root cause of such damages could be detected in a very early stage if you were monitoring the power quality. In the second picture on the bottom, you see also a device, is a voltage controller, which was exploded also because of power quality topics. So therefore, if we want to improve the reliability of our distribution system and especially improve or reduce, let's say, the non-conformance costs, we should deal with monitoring and classification of power quality. Of course, there are international power quality standards, and I have seen in my daily work that a lot of people are identifying power quality with harmonics. This means with harmonic distortion, but power quality is more. According to the definition of IEEE 519, power quality refers to a wide variety of electromagnetic phenomena that characterize the voltage and the current at a given time, at a given location in the power system. So it's not limited to steady state characteristics of the voltage. It's not limited only to harmonic distortion of the voltage, but we have also to consider the dynamic and the transient behavior of the grid and also especially of the voltage. Why are we focusing on the voltage? Because voltage is the most important criteria to evaluate the soundness of the distribution grid. And here you see the different areas which are dealing with characteristics of the power quality. First of all, we have the slow changes of the voltage deviations. We are talking about frequency deviations. We are talking about unbalance. But all of the three categories are dealing, let's say, with the fundamental frequency. Then the second category are the harmonics, which are normally dealing with harmonics up to the 50th harmonic, depending on the frequency. This is 2,500 hertz or 3,000 hertz. Interharmonics, they are really irrelevant when we are talking, let's say, about flicker or let's say direct connected inverters, which could also produce non-harmonic distortions. And supraharmonics describe or focus on the range of 2 kilohertz and above up to 150 kilohertz. So this is important, or this range gains importance in the future because we have a lot of active front ends in the future in our grid, and we have to deal with the frequency of the pulse width modulations of the inverters. So these are the harmonics, and then we have, of course, also dynamic or transient characteristics to consider. One thing, and I know this from my studies, is the impact of voltage dips or short interruptions on the power supply. Here, it's very important to know the size and the time to find the right mitigation measures. And of course, we have to deal with transients. This means we have to be aware that we have to investigate the transient characteristic of voltages or even currents with a resolution of lower than 1 millisecond. Most of the standards are providing limits and categories for those different areas. Here, the values which I have listed are referring to the standard IEC 61002-4, which is dealing with the performance of industrial grids. Then we have, of course, the European standard, standard 5160. Very popular is also, of course, the US standard IEEE 519. This standard is only dealing with harmonics, but also with current. But we should be aware that, let's say, the first priority to evaluate the power quality should be the voltage. So there are slight differences, but let's say I want to now to deal with disturbances, which with typical disturbances, and for this I have prepared examples. In my slide, there are some more examples, but some of them I will not describe here in my presentation, but I'm pretty sure that you will see this in the handout or even in the paper. So here is again a summary of the type of disturbances, and for each of that type, I have an example. The first thing, and this is something which was the focus also of our studies, especially in the industrial area of Karachi, is the handling of voltage sags. Voltage sags are voltage interruptions or low voltages caused by events in the upstream transmission or public distribution. The sign here, the arrow sign, should mean a short circuit current. In the industrial grid, we have, of course, drives. We have also very sensitive electronic devices. And electronic devices like inverters, they have two impacts on the grid. On the first impact, or let's say the first item which we have to consider, is that the inverters themselves are sensitive against distortion or disturbance of the power quality. On the other side, they are producing harmonics, and harmonics are also have an impact on the power quality. So they are both, let's say, a victim, but also root cause of power quality issues. And they have only a limited so-called false right-through capability. This means they have a limited voltage sex. In this example will also be zero, and due to the limited false right-through capability, we have to face outages of the drives and therefore also loss of production. How can we deal with this? This is very often the question of the clients. They want to improve their immunity against the consequences of the voltage sex. And of course, the solution is a UPS or independent power supply or a power stabilizer, which is limiting the voltage seg on the customer side. Here I have shown a typical solution which is applied on the medium voltage side. Why? Because most of the clients want to keep the process running for the whole plant, not only for selected processes. And this works like as follows. You have a flywheel or energy storage. You have a choke. These are these coils which we have, and the chokes have the task to damp the voltage drop coming from outside and to stabilize the voltage of the downstream grid. And you see here in the picture, these are now simulations that, let's say, a total loss of the voltage on the medium voltage side leads to a moderate voltage seg on the load side, and the chance to survive the outage is much bigger. Okay, this is a solution. What do you have to do for this? You need definitely statistical data of the voltage segs. You need information about the number, duration, and the severity of the voltage seg. Because if you want to handle 100% of those events, then this would get a very cost-expensive solution. But if you can improve at least the situation by 80%, then there are much more viable solutions, and you can specify the device. But perhaps you have handled, let's say, the 50 hertz voltage seg, but on the other side, there are new challenges with respect to the harmonic distortion, because you are now decreasing the short circuit power. This would mean you are increasing the short circuit impedance, and more interesting, you are shifting also the so-called resonance point in the grid. This would mean if you have harmonic sources in your downstream grid, and those harmonic sources are producing harmonics at a resonance frequency, then you have a high harmonic distortion. And this is exactly what happened here. So it was not sufficient to deal only with the voltage segs, but you also have to improve the harmonic distortion. And this would mean one has to find solutions like passive or harmonic filters, which are dealing especially with this harmonic distortions and to put this under the allowed level. To identify the right measure, of course, you have to carry out spot measurements to understand the different operation scenarios. You have to carry out the measurements to understand the harmonic distortion or sources, the drives. And you have to carry out simulations to determine the resonance points and to find the proper filter design. Or you can also split your grid if you have the chance to separate the sensible from the unsensible sources. These are the mitigation measures. Let's go to the dynamic part. This is also very common now that we are introducing more and more electronic devices, but these devices are not only inverter drives, but we are also talking about batteries, which you are using, for example, to flatten the peak power, or renewables, solar renewables, to compensate some of your demand. And here I have prepared an example of a data center. And in a data center, you have DC loads, which are supplied by UPS. This is the UPS. And you have, of course, emergency generators to be able to run the plant under island condition. And now following has happened. The client has made tests and under island condition. So this means the emergency load generation was more or less the same as the reg load, and suddenly we saw voltage fluctuations, we saw voltage oscillations, we saw increase of the voltage, and finally the UPS system drops because of overvoltage in the DC circuit. So these are things where the control strategies are not optimum. Where the settings of the controllers of the UPS were not adapted to the application case. What can we do here? Of course, we need measurements to understand what is happening. Then the solution would be to readjust the settings of the controllers, perhaps to modify the power factor control, the reactive power control, especially to reduce the gain or increase the time constants, so that we get at the end of the day damped oscillations and stable operation. This can also be investigated by transient simulations.
Can you hear me?
So, you see here, in every case, I mentioned measuring or monitoring. And if we want to prevent such faults, we need a permanent monitoring. This means we need fixed mounted monitoring devices, and we need stable communication channels to retrieve the data and to evaluate this. And
Dr. Blug, now you have 5 minutes to conclude your presentation. 5 minutes to conclude your presentation.
This is yeah, okay. This is sufficient. Yes. So you need the right measuring devices. You need the communication lines, and then you will see that you have to deal a lot with data. So, and our solution to handle those data, to identify distortions in a very early stage, is the application of AI. This would mean we were asking ourselves, how can we transfer our strategy to analyze anomalies, to identify signals, and to find the diagnostics. And we are doing this with AI, because AI provides algorithms which are perfectly matching that approach. And our solution is called power quality analytics. But I want to say to you, it's not 100% perfect, but at least we therefore we need definitely an expert for the final evaluation. But nevertheless, this saves a lot of time, 80 to 90% of our time, so that we can focus on the most relevant things. So, but once we have detected those issues, and this is my final slide, we have to talk about mitigation measures. And I want to emphasize that it's not sufficient to be an expert on one area. You have to cover all the disciplines which are related to the distribution grid. You need knowledge about measuring technology. You need experience about simulation. You need experience on protection, because protection is very often the reason for outages. You need, of course, switchgear and filter design experience. So, and that's the reason why our department is that big and worldwide spread, because we have to combine all those talents and expertises to find the final mitigation measures. And this is exactly what we are also doing with our colleagues in Pakistan. So I'm now at the end of my presentation. I hope I kept the time. I wish you a nice conference. And of course, if there are questions, I will be ready to answer this. Thank you very much. Okay.
For this presentation session, thank you, Dr. Saab. All the Q&A session will be conducted right now. So if anybody have any question, they can raise their hand. Any questions? Mike?
My question is, what is the role of equipment immunity in power quality issues?
Is the question audible to you, sir? जवाब दे उनकी आवाज नहीं आ रही.
So I'm audible, yes. So, and we have different electronic devices there, and we have different impacts from the steady state up to the transient area. So this is the immunity for, let's say, transients. We have to deal, let's say, with over voltages, transient over voltages, which can harm the insulation. And for harmonics, if we are talking about the impact on harmonics on the condition of the equipment, so we are talking about thermal impact on the condition of the equipment. I hope this is the right answer, or I have understood your question.
Are there any other questions for Dr. Christian Blug?
Actually, I would like to know one thing, that what is the maximum losses that your harmonics filters add to the equipment, like by adding your filter, what is the maximum losses, power losses?
So the picture is frozen, or I hear nothing.
Say it again. Actually, I would like to know that what is the maximum loss, energy loss in like after adding your harmonics filter, like what is the maximum loss that is being added to the system?
I can see you, but I cannot hear you.
Hello, sir, can you listen to me now? You can write the question in the chat, that what is the energy loss due to the addition of harmonic filters or SVGs. in the system?
The maximum energy loss due to any proposed harmonic filter. First of all, we have different kinds of harmonic filters. Passive filters and active filters. Let's talk about, first of all, passive filters, which are especially applied in the medium voltage or even in the high voltage. Very often, those filters are combined with, let's say, capacitor banks, because you need capacitors, and the goal of those capacitor banks is to improve the power factor at a fundamental frequency and to reduce the harmonic content and the harmonic voltages. So this would mean that such kind of filter would definitely reduce the energy losses, because you are reducing the reactive power, and by reducing, let's say, the harmonic current over the upstream transformer, you are also reducing losses, for example, due to the skin effect and those things. So therefore, from our point of view, we are not dealing, let's say, with additional energy losses of active filters or filters, because the application provides already a better operation with low losses. So therefore, the internal energy losses are not relevant in the whole context.
Any further questions from the audience? We have one more question that is being written in the chat. Sir, if you can please answer that.
Okay, now I can hear you. Is there any required immunity level for voltage dips? We are following very often the IEEEP curve. This is a immunity curve which is applied, for example, for IT equipment, and that equipment or that curve requires, let's say, a residual voltage of up to 60% for durations of a voltage like higher than one cycle. So this is a very challenging requirement. Nevertheless, inverter drives are able to have a better fault rate through, but nevertheless, this is the immunity levels which we are following.
Thank you, Dr. Christian Blug. It was a wonderful session with a deep insight on the power quality. We thank you once again for sparing for your time for our symposium. Thank you a lot. Thank you.
Bye-bye.
Now,